Hello, everyone. Hello, my SPE students. I miss you all so much, Rami and everyone. Rami, Firas, Muhammad, Omar, Abdurrahman, and Tala, of course. I miss you all very much. I wanted to record this session today as quick as possible because of your next exam, which is going to be on the day after tomorrow. I want you at the time being to review most of our course PDFs and contents. You will find all of this perfectly on Moodle. The Moodle platform for SVE is wonderful. It contains all the previous exams with a detailed explanation of the solutions and the resolutions with each chapter. So I want you to study first, read the PDFs very good, then start writing and start solving these problems. I know it's never too late, so you still have the rest of today, tomorrow, and hopefully you will be in a very good shape. The slides of this session, I will send it to you directly, and the recorded session, it will be on the YouTube, as you know, always on the playlist. So I want to go through an overview of our course. Of course, that's a small one, so and I will try to solve also a recent exam, one of the previous recent exams. And you will find it on Moodle with the solution on one of the PDFs, on the PDFs part in LMS. I'm sorry, on Moodle. First of all, before you start working with exams or tests or whatever, you should do the following. First of all, review our course contents. You will start by the matrices, properties, and applications. All the properties and the operations, you should review them. Linear transform and application on the Lin-Tooth matrix. The first part or the first chapter, you can go through it as quick as possible about the types of matrices, the properties of each matrix, the general knowledge about the operations. This is going to be really very quick. But I want you to re-watch the recorded session of Lin-Tooth matrix with the details of this session. I believe it's a couple of vids. You will find them on the YouTube. Please go through them and try to resolve the problems introduced at this part and the exercises that we did solve together. Also in the revision session, you have more than one vid and more than one exercise solved till the end about the Lin-Tooth matrix and the inverse Lin-Tooth matrix also. So it's really very important to watch these videos once more. Also, the vector spaces and sub-vector spaces, going through the vectors, how to be sure that you have a linearly independent set of vectors. They are not dependent, it's a dependent set of vectors. How a vector belongs to a sub-vector space or a vector space. How to check if a vector is not a part of a vector subspace and so on. The basis, how to get the coordinates of vector space. Then going through the eigenvalues and eigenvectors. This was by the end of our course, how to get the eigenvalue for a matrix, what the characteristic equation, how to handle it, how to deal with it. All of this is really very important. Remark also the properties of evaluating eigenvalues and eigenvectors, like the sum, if the sum of the columns or the sum of rows equal to a certain number, probably this number is going to be one of the eigenvalues. Please do check all of this. We did go through it plenty of times, especially in the revision sessions that you will find already recorded and on YouTube. Also, don't forget to watch the whole vids of the dynamical systems about moving from A to B and the relations connecting these systems together. This is really a very important video. Also, I want you to look at it before you start any work with previous exams or tests or whatever. This is really very important. At the time being, I want to talk with you a little bit and refresh your information about the reset exam of 23, 24, I'm sorry. So, and it will be a model for the next sitting, inshallah, the reset exam. For the first paper, or the heading of this exam, it's stated, of course, the academic year, whatever. This is one of the versions. It's really also about that time. It was in the last year, about 18th of Jan. Ours will be by the 14th of Jan, so just only 4 days earlier than this one. Identify the version of your exam on the first page of your answer booklet, so you should write that. I will give you the booklet. Either you will have two options actually, but I'm just waiting till we end the design of your exam. So in between, either you have your exam paper, and I will give you a solution booklet with the drafts and everything. Please don't write anything out this draft part, and it will be written on this exam booklet, how to go through it, how to solve, where to solve, and everything. So between this one, or to have each question and a space beneath it in order to write whatever you want with respect to the solutions. The major issue that I want to mention at the time being, and I want it to be recorded for the next semester or for next sessions, mainly, please don't use any paper outside the booklet, okay? So all your drafts, whatever, you want to sketch something, you want to write something, just do it with the exam booklet. So identify the version of your exam on the first page of your answer booklet. Write your name, student number, of course, the ID, which is listed ID, and the group to which you are answering this question. Don't answer two more than one group per one sheet, so don't mix the questions. For us, I will make the first paper about group number one, then you will have each group specified in a specific place in your exam booklet. Use both sides. For us, we will use just only the front page or the front side, because I will scan all the results, as you know, to be with us as a soft copy from your resolutions. Don't unstable the answer booklet, blah, blah, blah. You know all of this. Always provide a careful justification for all your conclusions, except group one, which is a multiple choice, so you can actually access it without the details. But I would prefer, if you like to write anything about any question or something, just use the paper with you or your paper to write it. I want to look at it, okay? It will be also a defense for you for the problems, in the case of the problems that contains many steps, okay? So anything related to any question or any group of questions, please write it in your answer book. For this question, is stating that consider the inverse Leontief matrix. So stop. I will go through my chapter or the course. I will stop by Leontief matrix, and I will bring all the information about Leontief matrix. So consider the inverse Leontief matrix. In specific, he's talking about the inverse Leontief matrix. Okay, which is given to you 2.2, 1.7, 1.3, and 3. How much does the production of good 1, okay, increases to you a unitary increase in demand for good 2. So if good 2 increases by just only 1 unit, what's going to be the effect in production of group 1 or good 1? So the inverse Leontief matrix, if you remember, this is the Leontief model, which is x equal to ax plus d. So if I want to get the inverse Leontief matrix, all I have to do is to get the production as a function in demand, as of course, as you know. So I've just moved ax from the right hand side to the left hand side. Taking x as a common will leave me with I minus a, multiplying both sides by the inverse, and this is why it's an application on matrices. I will get the inverse matrix. Now, remark and read carefully. I have the inverse of Leontief matrix given for me. Also, there is a remark I want to keep it in mind, that the rows of the length of matrix represent the goods being produced, and of course the columns represent the goods being demanded, or what's demanded. So simply for a unitary increase in demand for good number 2, it means for the second row. So if you get the inverse length of matrix and you multiply it by 0 and 1, as we are talking about the demand of the second good, so you will end up having 1.7 and 3. Just multiply the first row by 2.2 times 0, 1.7 times 1, so it's going to be 1.7. Then for the second row, 1.3 times 0, 3 times 1, which will give you this shape. So increasing the demand by a unitary one or by a unitary unit, it will lead to an increase in the production of the first good by 1.7 and an increase in the production of good 2 by 3. He is asking you about the increased unitary blah blah blah. How much does the production of good 1? So we are asking about good 1. So specifically, it's going to be 1.7. We can also get it from this matrix. This is the rows, which is the productions. These are the columns, which stand for the demand. This is why I've given you this remark. So simply, it's going to be the first good and the second demand by 1. So it's going to be 1.7. So now the answer is number B. The major issue, it's not about solving this problem. The major issue is how to call back your information. I will have to find first which chapter, at which specific part, and you will make things easier for you to remember what's this all about and so on. For the second problem, is asking you what's the dimension of the vector space of a 2 by 2 matrix. But this is not just only any matrix, it's a specific matrix. It's an anti-symmetric matrix. Okay? Yes? Yes? Anti-symmetric matrix. And in order not to confuse you, he's telling you that anti-symmetric matrix, which is a skew-symmetric of course, is proving that A transpose equal negative of A, which is the probability of a skew-symmetric matrices. So all I have to do is to remember what's a 2 by 2 skew-symmetric matrix. Any skew-symmetric matrix, or a 2 by 2 skew-symmetric matrix, it's gonna be on this form, 0, 0, then I will have this value, which is A of 1 and 2, I will have the opposite value on the second row. So it's going to be negative A1, 2. This is a form of a skew-symmetric matrix. From a first look to this space, it can be A1 and 2 times 0, 1, negative 1, and 0. So the basis for this vector space, it's going to be just only this element or this vector. So the dimension will be just only one vector. So I believe it's going to be 1. Remark, this is a little bit tricky question, because once you say I need the dimension of an n by n matrix, a square matrix n by n, it's going to equal to n to the power of 2. So if I have a 2 by 2, it means I'm in 4 dimension 4. But he stated that this is a specific case while you have anti-symmetric matrices. So an anti-symmetric matrix in the skew-symmetric matrices, in general, form 2 by 2 anti-symmetric matrices is in this form, 0, A, negative A, and 0. So if you take A as a common, you will end up by having the vector and the basis for this subvector space. In general, dimension of a vector space 2 by 2, it's going to be 4. But this is a special case, as I told you previously. So this is the basis of this vector space. And so the dimension will be 1 dimension or dimension 1. So the right answer will be D. More than perfect. Okay, before going to the next question, I want to review with you how the set or the solution set of a general system of equations can be classified or can be obtained. If you remember this form, which states that the solution set of any system of equation, it's actually a particular solution, okay, and the null space of this system. The null space is the homogeneous solution of this system of equations. We already did go through this plenty of times, and also in the previous revision we explained this, how the final solution of a system of equations can be derived. So once more, remember this slide. I've actually brought this slide from the lecture of this part. So classification of a system of equations based on the spaces. I will have the solution set space, which equal to the particular case or the consistent independent set plus a null of A. Remember that for solving a system, B should belongs to the column space of A. If B belongs to the column space of A, then you will have a consistent system. Either the consistent system will develop a consistent independent or a consistent dependent system. But it's a condition to have a solution mainly for a system of equations. But on the other hand, if it is inconsistent, which means that B doesn't belong to the column space of A, then you don't have a solution. You have inconsistent system of equations from the start. Okay, once more, if I want to find the null of A, which is the solution of the homogeneous part, as I told you, if the null equal to 0, you will have consistent independent system. If the null doesn't, it has a solution or it has values, so it has a dimension greater than 0, then you will have a consistent dependent system. The question here is really very nice, and he's asking you, this is a solution set for a certain system of equations, 3 by 3. And it has x as the solution vector or the solution set, 1, 0, 2, plus an alpha, where alpha belongs to R. It's an infinite number of solutions, of course. This is why you have the null solution here in front of you, 0, 1, and 0, 0, 1, and 0. And he's asking you, is a general solution of a system AX equal B? So it's a solution for certain system of equations. Which of the following matrices could be its augmented matrix? Which one of these matrices could be the augmented matrix of this system? This is really very simple. All I have to do is to look carefully to each one of these augmented matrices. This is, of course, the coefficient matrix, and that's the column or the result column of this matrix. And specific for C, this is stand for no solution. So in anyhow, this is not gonna be the case for infinite number of solutions. So this is completely rejected, C. If you look at D, you will find the coefficient matrix is a 3 by 3, okay? It's a rank equal to 3, and the rank of the augmented matrix is also 3. So this augmented matrix is actually on the reduced echelon form, and it is relative to a unique solution or a consistent independent solution. So this is inconsistent system, this is consistent independent solution. Leaving me with A and B, okay, if I want to look by inspection. Looking for B, for example, you will find that you have a value of the first variable, you are missing the second variable, and you have the last variable. So if I look to the first variable, it's gonna equal to x, for example, equal to 1, which is a number. And for y, or for z, I'm sorry, it's gonna equal to 2. But I don't have y in here, which means y will be the free variable, or y will equal to c. So this will leave me with a particular solution. If I want to expand this matrix, it's gonna be on this form. It's gonna be x equal 1, for example, if the variables x, y, and z. I don't have a y value, then I will have z equal to 2, but I'm missing y, there is no y here, and there is a complete row equal to 0, which is standing for a consistent infinite number of solutions. That's y equal to y or a certain constant. If I want to write this solution set on the solution set general space, it's going to be the particular one, which is 1, 0, and 2, and this is for the xp part, plus I will have 0, y, and 0, which is going to be put on the form 1, 0, 2, and plus certain constant, let's say c belongs to r, and I will have 0, 1, and 0, and this is the null space. If I compare this with what he is giving me, now I know that's B is the correct solution. So either by inspection or by understanding the following. So first of all, without going into more details, we can answer this question either by what previously introduced in the system of equations, looking carefully for each coefficient matrix and the result and comparing them exactly as I did with you. There is another way just to go through this from the good understanding of the solution set. So all I have to do is to take the augmented matrix and then multiply it by 1, 0, 2, which is the particular solution, which is going to develop 1, 2, and 0. And if I multiplied the coefficient matrix by 0, 1, and 0 column, you will have the null solution, so which stands for B is the solution based on the previous slide. Okay, perfect. For the last question, it's about linear transformation. So let T a linear transform from R3 into R2. And it's a linear transform, and UV belongs to R3. So both U and V are R3 vectors. Knowing that the T of U, the transform of this vector, it's going to be 1 and 2. The transform of V is going to be 2 and 1, which is the image through T of the vectors U minus V. This is really a very nice question. This question is about the properties of a linear transform, which preserves the addition closure and the multiplication by star. So simply, all I have to do, as I told you, this is a very nice question. It's targeting the understanding of a linear transform. So being a linear transform, it means it can handle addition and multiplication by scalar. So it's simply T of U plus alpha times V, where alpha equal to -1, which is going to equal to T of U plus alpha times TV, which is going to result to this result. This leaves us with the following, that we can say that the transform of the first vector, which is going to be 1, 2, minus the transform of the second vector, which is 2 and 1, leaving me with -1 and 1. So the image of the transform of the difference between these two vectors is going to be -1 and 1. And so problem number B, or choice number B, will be the tempting question now. From this set of questions, what I want you to keep in mind is how to think about them. Just to start with remarking each part, try to recall the information regarding this chapter, and start step by step going through each part of the question, read it very carefully, and hopefully you will find the answer as quick as possible. For group number 2, and of course for the first group, it's going to be on 1 page. I will support a draft paper for it. If you like to make calculations or something, please do it within the answer booklet. For the group number 2, he's targeting, let's see, he's giving you a matrix A, which is 2, 0, and 1, 0, 1, 1, 0, 1, and he's asking you a direct question about finding the eigenvalues of A. So this is really a very simple question. If you remember, in order to find the eigenvalues, so now I'm going to go to the part of the eigenvalues. If I want to go and find the eigenvalues of a certain matrix, all I have to do is to recall the characteristic equation, which is very, very simple. A minus lambda I the determinant equal to 0. So it's really very simple. All I have to do is to get this determinant equal to 0. And here it's going to be a 2 minus lambda, 0, and 1. For the second row, it's going to be a 0, 1 minus lambda. Then I will have 1. For the last row, it's going to be also 0, 1 minus lambda. And I will have 1 at the start. I'm sorry. This is, yes, exactly right. 1 minus lambda. So start by multiplying the principal diagonal, if you like to do it this way. So I will have 2 minus lambda times 1 minus lambda square. Then I will go for the bottom base times the vertex of the other triangle. So it's going to be 0. Same way like. And for the negative direction, it's going to be minus 0. Then minus 2 minus lambda, as you can see. And the other direction is going to be 0. Now I will need to handle this equation. Simply take 2 minus lambda as a common, when this will leave you with 1 minus lambda squared minus 1 equal to 0. And continue the analysis, you will find lambda equal to 2 and solve this quadratic equation, which is lambda squared minus negative 2 lambda plus 1 minus 1. They will eat each other. So I will have lambda squared times lambda, 2 minus lambda equal to 0, which will leave me with lambda minus 2 to the power of 2 equal to 0. And this means lambda equal to 0 and lambda equal to 2. Repeat it 2 times, which means the algebraic multiplicity m of a, the algebraic multiplicity for 0 is going to be 1, and the algebraic multiplicity of 2 is going to equal to 2. This is the details of evaluation of the eigenvalues, if you remember. So simply, I will try to get the characteristic equation, then determine the eigenvalues, check the algebraic and geometric multiplicity. This is easy by finding how much is repeated or how many times it is repeated, the final value. So I will start with the characteristic equation. As I told you, determinant of a minus lambda I, which can be put on this form, exactly like what we did. I will try to multiply them. Here I used Sar's rule, if you remember, but also I can use the Gauss formula. So I will go through by the first row. So I will use 2 minus lambda, then eliminating row and column, and this is what I will have: 1 minus lambda, 1, 1, 1 minus lambda. So it's going to be on this form. Then I will try to continue expanding. So it's going to be 2 minus lambda, negative lambda, lambda minus 2, leaving me exactly as we saw together an algebraic multiplicity for lambda equal to 0, which is 1, and for lambda equal to 2 is multiplicity of 2 because it's repeated 2 times. If I want to get the eigenvectors, you know that the steps are really very easy. All I have to do is to set the system, if you remember, for lambda equal to 0, for example. So I will have a system like this. This is the infinite number of solution of the null space of this matrix. So it's going to be a 2, 0, 1, and 0. For the second row, it's going to be a 0, 1, 1, and 0. And for the last row, it's going to be a 0, 1, 1, and 0. And once more, I will start to use the magic of getting a reduced echelon form. I have 2 identical rows, so simply all I have to do is to just multiply the second row by negative, add it on the last row, so I will have 0, 0, 0, and 0. Now I'm trying to get u1, which is the eigenvector 1, that corresponds to lambda equal to 0, the first value, so I'm just substituting. And for the row here, it's going to be 0, 1, 1, and 0. Then, for the first row, I will divide by 2. So it's going to be a 1, 0, half, and 0. Now try to expand it once more in order to get the relation between the components of this eigenvector. So I will say this is eigenvector first component, eigenvector second component, and the eigenvector third component, leaving me with the following: u11 will equal to negative 1, 2, u1, 3. For the second row, u12 will equal to a negative of u1, 3. So having a vector with 3 components, u1 sub 1, u1 sub 2, u1 sub 3, start substituting by these values. u11 will be replaced by negative 1 over 2 u1, 3. And for u12, I will replace it with negative u1, 3. And this is u1, 3. Let's put u1, 3 equal to 2 or something to avoid the fraction here. So I will have negative over 1 and the negative 2 and 2. That's a form of this vector, if you like to do it this way. Okay, so actually that's the form as I told you. It's going to be a negative 1 here for me, negative 1, negative 2, 2, or simply multiply in a negative sign. You will have exactly the same. It's up to you. It's an infinite number of solutions. You can manipulate it as much as you want. And for lambda equal to 2, it's going to be exactly the same steps, but I will replace these values equal to 2, and they will end up having this eigenvector. The problem here that once you evaluate the eigenvectors, you will be able actually to answer the second question. So he asked you about the eigenvalues. We already have the eigenvalues. We now know their algebraic multiplicity. He is asking you about show that A is not diagonizable. When A is not diagonizable, A is not diagonizable if you have a mismatch between the algebraic multiplicity and the geometric multiplicity. The geometric multiplicity is the dimension of the eigenvectors that you are getting. So the eigenvector space of lambda 2 is 1, while the algebraic multiplicity of this value is 2. So this is why you can't get a diagonizable matrix or do a diagonalization for this matrix. So once more, it's not diagonizable. You can check the spelling, I believe, I'm not really sure. Okay, diagonizable because the difference in multiplicity, algebraic and geometric, as we saw previously. So if I want to check at 2, I will do exactly the previous steps. This is the system augmented matrix. After substituting by 2, so it's going to be a 0, negative 1, and the negative 1, exactly like this one. I will start to do the row operation in order to get the reduced echelon form, from which we can get the form of our vector. So starting from this step, replacing the third row instead of the first row, as you can see, multiplying the first by a negative 1, then adding the first row and third one, we will have zeros. Then I will multiply the first, or add the second row on the first row. I will get the reduced echelon form, as you can see, which states that it's going to be x, the free variable, and y equal to z and z equal to z, which will leave me with this vector, which is dimension 1. And as I told you, there is a mismatch between the algebraic multiplicity of eigenvalue 2 and the geometric multiplicity. The geometric multiplicity is the number of vectors that's in the basis of the eigenvector space. Here is 1. Why? The algebraic multiplicity is 2 because it's repeated 2 times in the main solution. So, as you can see, there is a mismatch, and this is why it is not diagonizable, as we say. Okay, change the entry for number C. He's asking you to change the entry of A13 in order to make A is a diagonizable. So all I have to do is to regain this matrix, the main matrix, and for element A13, this is first row, third column. So this element should change, and to see what's going to be. Okay, I did that already. To make that diagonizable, we should change the element A1C to a certain value. So I'm going to consider it by K at the solution you have in the PDF. But there is a remark here. Changing this value is not going to affect on the values of the eigenvalues. It will stay the same. Also, lambda equal to 0 and lambda equal to 2 with the same algebraic multiplicity. But I will need to choose this value wisely in order to have a geometric multiplicity equal to the algebraic multiplicity. So all I have to do is to start once more from the system and try to put it on the reduced echelon form. So I will start with this matrix, substituting by 2, which is the problem exactly, that the algebraic multiplicity at 2 doesn't equal to the geometric multiplicity. So I've substituted by lambda equal to 2, this is the main form. I will leave k as it is, just to give me the condition for this value. Start to work your magic, just replacing the last row instead of the first row. Once more, add these rows together, you will get a zeros in the middle row, but the one that I'm searching for in the last row, which is 0, 0, and k. Now, if k equal to 0, then I will have a geometric multiplicity of 2, because in this case, x will equal to will be a free variable, and also y will depend on the values of z. So if I took the last one, I want to show you this. I want to show you if k equal to 0, how to have a geometric multiplicity of 2 equal to the algebraic multiplicity. I want to show you this. It's really very simple. All you have to do is to make a substitution by the value of k which equal to 0, and then try to get your solution. So, step by step, I want to show you this. All I have to do, if k equal to 0, this matrix is going to be on the form 0, 1, and the negative 1. I will, of course, this is the result column. This is the coefficient matrix. The second row is 0, 0, and 0. The last one, once k equal to 0, so it's going to be zeros. Try to expand the solution set. So you will have u1 first component equal to itself, while in the second, which means u1